Good morning, one and all. Today we will see the next chapter, chapter number 4, antenna array. In the antenna array, we will going to discuss about the different types of the antenna in a array formats, and we will going to discuss how it will be behave. What are the mathematical backgrounds be created of this type of the array antenna. See, array of the two isotopic point sources. Basically here there are the two isotopic point sources which is separated by the distance d with reference to the central point with respect to isotopic point source 2 is the d by 2. Similarly, the distance from the isotopic point source 1, which is again d by 2, then this distance d by 2 and d by 2, the overall distance between the 2 points is d. And at a point P we at a distance point P we have able to measure the electric field E. Basically, in the form of the array of the two isotopic point sources, the equation is that E, which is equal to here E, which is equal to E0 e raised to minus j br1 plus E0 E minus j br2. Basically, E0 is the unit distance electric field E, and e raised to minus j and e raised to minus j br2 and br1 means one electric field is basically the isotopic point source 1. This is the isotopic point source 1 and isotopic point source 2. This isotopic point source 2 is advanced and isotopic point source 1 is the retarded. It is the advanced by the 90 degree or any phase phi, and isotopic point source 1 is the retarded. Basically, the equation E, which is equal to E0 e raised to minus j br1 plus E0 e raised to minus j br2. Beta is the phase constant which is equal to K, which is equal to 2 pi by lambda. Lambda is the wavelength of an antenna. Then R1, which is equal to R plus d by 2 cos phi, and R2, which is equal to R plus d by 2 cos phi, and R is the greater than or equal to D, because basically we are able to measure this distance R and this distance R from the central point P. At a distance point P we have able to measure the electric field E. Okay, then here the angle you have to be able to measure. Basically, this is the x-axis and y-axis, and from that x-axis and y-axis there are the two electric field at a position 1 as well as at a position 2. Then E, which is equal to E0 e raised to minus j br e raised to minus j b d by 2 cos phi plus e raised to plus j d by 2 cos phi, which is equal to E0 e raised to minus j br e raised to minus j psi by 2 plus j psi by 2, which is equal to the resultant electric field E. Then with reference to here psi, which is equal to beta d cos phi, and beta is the phase constant, its value is given b, which is equal to k, which is equal to 2 pi by lambda, means here is b d cos phi 2 pi d and b, which is equal to 2 pi by lambda, hence it is 2 pi by lambda d cos phi. Then the final expression we have seen here, E, which is equal to 2E0 cos psi by 2, which is equal to 2E0 cos pi d by lambda cos phi, because psi, which is equal to dr cos phi, and dr cos phi is the distance at the central point. Dr is nothing but you are able to measure the distance at the central point at a point P at a distance. This distance is the dr cos phi, and while normalizing this equation, E, which is equal to 2E0, and we have taken the 2E0 which is equal to 1, hence this equation E, which is equal to cos psi by 2. then we will going to discuss about it. The final expression is the while after the normalizing the equation, after normalizing the equation here, E which is equal to cos dr cos phi upon 2 and dr which is equal to 2 pi d by lambda and 2 pi by lambda which is equal to beta d and d which is equal to lambda by 2. After normalizing, see E which is equal to cos, basically here is the 2e0 cos dr by 2 cos phi, but after normalizing the equation 2e0 which is equal to 1, hence the equation is E which is equal to cos dr by 2 cos phi, dr which is equal to 2 pi d upon lambda and 2 pi lambda which is equal to beta d, d which is equal to lambda by 2, d which is equal to lambda by 2, then we have able to substitute the equation d which is equal to lambda by 2 in this equation, then dr which is equal to 2 pi, d is a lambda by 2, means lambda gets cancelled, then 2 gets is again cancel out, then pi by 2, E which is equal to cos pi by 2 cos phi. This is the equation. Phi which is equal to E is 0 degree 1 and E is a 0 for 0 degree because cos 0 which is equal to 1, cos 90 for this equation cos 90, if this angle is the 90 degree then resultant electric field E which is equal to 1, and for cos for 60 degree E which is equal to 1 upon root 2. Then your half power beam width is 60 degree in the one plane and 360 degree in the another plane. And for this case what we obtained, if the two isotropic point sources of the same amplitude and the same phase, the radiation pattern is along the y-axis, this is the along the y-axis, and for this case at a 0 degree where the zero electric field should be available and which is maximum along the y-axis, hence the figure of 8 radiation pattern we want to getting along the y-axis. This is the radiation pattern. For the next case we have seen the two isotropic point sources of the same amplitude but opposite phase. In case of the opposite phase, the radiation pattern is same radiation pattern, its meaning is that figure of 8 radiation pattern, but it is just opposite. For the previous case it is along the y-axis, x-axis, along the x-axis, means radiation pattern we want to getting along the x-axis at an angle of the 0 degree instead of the 90 degree. Thanks for the watching. If any suggestions, you please give the feedback. Thank you very much.